ladies and gentlemen. We already heard something about battery cell production this afternoon. I will focus on a very specific part of the manufacturing chain, which is the electrode slurry processing. This is one of the most critical steps for the production of the electrode. And in my talk, basically, I would like to cover two topics. First of all, I would like to elaborate on the basic concepts and unit operations which are used for electrode slurry processing. And in the second part, I will present a fully continuous mixing process which we have developed for the large-scale production of electrode slurry. So let me shortly introduce the Bühler company. We are a family-owned Swiss-based company, so we are located in the eastern part of Switzerland, in Uzwil. We have about 11,000 employees worldwide. We are active in more than 140 countries. And last year we have generated a turnover of about 2 billion Swiss francs. So Bühler is basically a process solution provider for many different industries and sectors. On the one hand side for the food applications, such as, for example, the processing of grains, of chocolate, pasta, coffee, and so on. But we also have an advanced materials division where we are working on aluminum die casting processes. We have a vacuum thin film equipment unit, and I belong to the wet grinding and dispersion part of the division, where the battery application is one of the topics which we are working on. So although Bühler is typically not visible to the final customer, many of the everyday products you get in touch with, which you see here, are processed with Bühler equipment at a certain point of the value chain. So for the battery application, we mainly have two touching points. First of all, we provide wet grinding equipment on the left-hand side. This is used basically for the production of active materials, so for anode and cathode, and the precursors thereof. For example, for cathode, we have LFP materials or the precursors which need to be ground to a certain particle size. It's typically in the order of 200 nanometer. On the anode side, for example, we have projects where we need to grind silicon as an active material. And even on the separator material, we have some materials which need to be dispersed, ground in a mill. For example, the ceramic coating on a polymer substrate needs to be processed on an agitated bead mill. Then the second application on the right-hand side, the mixing, dispersing of the electrode slurry. Here we basically have two approaches. First, for lab pilot and small-scale production, we have a collaboration with the Japanese company Primix. Basically, we are the exclusive partner for this piece of equipment in Europe and Northern America, but we also built a complete system around, so we do not only supply the single machine, but we can also supply the complete plant, including raw material handling, storage of the final product, and so on. Then the second activity, this is a large-scale production equipment. This is the fully continuous mixer. This is a technology which we have developed over the last 6 years together with an Asian cell manufacturer. And in my talk today, I will mainly focus on this technology here. So what is the main challenge for electrode slurry processing? I believe the target is to reduce the operation and investment costs, and at the same time we need to make sure that the quality of the product at least remains the same level or can be even improved. So we are convinced that with the conventional mixing technologies in the market today, so the batch mixing systems, it will not be possible anymore to fulfill the requirements of the future applications for large-scale production, such as, for example, the electromobility or the energy storage solutions. That's why we as Bühler have decided to go into the development of this fully continuous mixing process, which allows to achieve very high productivities and at the same time maintain or even improve the quality of the electrode slurry. So let me shortly illustrate this with a small example. All of you know the Tesla Gigafactory. You already heard this facility today. This facility has a final capacity of 35 gigawatt hour, annual production capacity. And this corresponds to about 70 million liters of electrode slurry, which need to be produced per year. If you calculate this as a productivity number here, this will give you 12,000 liters of electrode slurry per hour. So that's quite a substantial amount of material which need to be processed. And if you want to do this with batch processes, you will need at least 24 of these very large batch mixers, these planetary mixers, and you can imagine this will not be the solution anymore in the future. So for the manufacturing of lithium-ion battery cells, you have different processes and intermediate materials involved. So we typically start with the raw materials. So on the one hand side, we have the active material, which is responsible for the storage of the charge carriers, so the lithium ions. We have some conductive additives, which make sure that the electrical conductivity in the electrode is ensured. We have some binder, which makes sure that the cohesion between the particles in the electrode and the adhesion to the substrate is guaranteed. And last but not least, we also have a liquid, a solvent, which is on the one hand side used to dissolve the binder or a thickening agent. And on the other hand side, it's also used as a carrier for these solid particles to the electrode of the battery. So all these components have to be brought together in the so-called electrode slurry here, which is subsequently coated on the electrode, dried, calendared, slitted, and finally assembled to the final cell here. So the distribution and the dispersion degree of the solid particles here in this electrode slurry has a significant impact on the microstructure of the electrode here, and therefore on the final performance of the battery. So let's have a closer look at this electrode slurry preparation process. So what are the main tasks for the electrode slurry preparation? First of all, we need to make sure that all solid components are properly wetted or dissolved in the liquid phase and homogeneously distributed. The solid particles in the form of dry powders are often held together by strong attractive forces, for example, the van der Waals forces. So these agglomerates need to be deagglomerated to the required particle size. And last but not least, for the subsequent coating step, we need to make sure that the electrode slurry has the required viscosity, is sufficiently stable, and all the gas bubbles are removed. So the unit operations to fulfill all these tasks are basically dosing of the raw materials, so the liquids and solids, then the dissolving of the binders and thickening agents. Then we typically have a premixing step, which either can be wet or dry. Then a fine dispersing step, which finally determines the quality of the slurry. And before we go on the coating line, you need a degassing in order to get rid of the gas bubbles. So for lithium-ion battery slurry production, you mainly can distinguish between two approaches. First of all, we have the high solid content kneading process, and the second one is the high-speed shearing process. So in the battery industry today, the typical equipment for the high solid content kneading process is the planetary mixer, as shown here on the left-hand side. And for the high-speed shearing process, you can, for example, use agitated bead mills or high-speed mixers. So the main difference between these two approaches are basically that the dispersion of the solids takes place at high viscosity and relatively low shear rates for the high solid content kneading process. And for the high-speed shearing process, you have relatively high shear rates and low viscosity. So these are the main differences between these two approaches. Furthermore, for the high solid content kneading process for the planetary mixer, this is a batch process whereby the high-speed shearing process also can be conducted in a semi-continuous mode. On the other hand, the fully continuous mixing process enables to combine different sequences of kneading and high-speed shearing in a single device, and this gives you then several advantages for the processing of the electrode slurry. So our solution, the Bühler solution, is based on a co-rotating twin screw extruder, which basically combines the continuous dosing of the raw materials, so the powders and liquids, the premixing, fine dispersing, and even degassing in a single device, fully continuously. So the main difference compared to the batch mixing process is the short mixing time. So we're talking here about 1 minute of mixing only. And then the final product comes out of the mixer. So let's have a closer look at the differences between batch and continuous mixing. For the batch mixing process, basically you have two steps involved. First of all, we have the addition of the pre-weighted amount of solids and liquids, followed by the distribution over the whole volume of the batch. So in order to achieve the requested quality or homogeneity of the product, typically several hours of mixing are needed. So we're talking about 4 to 6 hours of mixing time at production scale. On the other hand, for the fully continuous mixing process, we have the continuous dosing of the solid and liquid raw materials, followed by the micro distribution in the continuous mixer here. So due to the fact that the fully continuous dosing of these raw materials already take a major part of the mixing work, the mixing time in the mixer itself is reduced to in the order of 1 minute only. So here we have 1 minute, here we have several hours of mixing. By varying the process parameters of the continuous mixing process, such as, for example, the speed of the screw or the configuration of the screw or the solid content along the mixing zone, this enables to very accurately control the shear load which is applied to the product, and this is very important. I will come back to this topic later on. So on the left-hand side, you see a cross-section of the mixer here. So in the middle, these are the screw elements, and the actual shearing of the product basically takes place in the gap between the screw elements and the barrel wall here of the extruder, and also between the screw elements here in the middle. Another important feature of this technology is that you have a relatively small active mixing volume. As a result, you have a very narrow residence time distribution, which helps to improve the consistency of the product which is coming out of the mixer. So today, the maximum production capacity which can be achieved with a batch mixing system is in the order of 500 liter per hour. This is really the upper limit which you can do. If you want to go higher, you need to multiply accordingly. On the other hand, for a fully continuous mixing system, you can go up to 2,500 liter per hour for the slurry production. So due to the high productivity, this means that you can replace multiple batch mixing systems with a single continuously operated mixing line. Again, if we take the example of the 35 gigawatt hour capacity, the 70 million liters of electrode slurry, we have this 24 batch mixing systems. On the other hand, 6 continuously operated mixing lines only. As you can see here already, beside the number of mixing lines, this has also an impact on the space which is required on the installation. As a result, the investment for this mixing equipment is reduced by about 60% for this 35 gigawatt hour capacity, from about 16 million to 24 million with the continuous mixing system. So this is the first big advantage then for the cell manufacturer for this continuous mixing system. And furthermore, another important aspects are the operation costs. So for example, we have conducted several studies at production scale comparing the specific process energy which is needed to achieve a certain quality of the product, and we could show that for the batch mixing system we have about 75 watt-hour per liter of electrode slurry, whereby for the continuous mixing system we can reduce this energy by about 60%. Then some of the active materials are moisture sensitive. You heard this already today. So this means some of the equipment has to be installed in a dry room. So due to the smaller footprint caused by the smaller number of mixing lines of the continuous mixing system, this also has an impact on the volume of the dry room itself, and therefore on the energy which is needed to maintain the dry room climate. So again, a small example with some numbers here for 12 lines for this 35 gigawatt hour capacity. For the cathode in this case only, the anode side would be a water-based. That's why we only have 12 lines here. This corresponds to about 9.1 gigawatt hour energy consumption of the dry room only. With a continuous mixing system, you can reduce this down to 3.6 gigawatt hour. Due to the high degree of automation of this continuous mixing system, this also allows to reduce the number of operators, so we're talking about 50% here. And we also have conducted several studies on the effort which is needed to clean the system. This is always an important point when you talk about production of electrode slurry. So as an example here, for a 500 liter per hour capacity, you need about 5 hours of cleaning for the batch mixing system, involving a solvent consumption of about 300 to 500 liter of solvent, which is quite a lot, especially if you're talking about NMP for the cathode. On the other hand, due to the relatively small active mixing volume of the continuous mixer, you can reduce the required amount of solvent down to 50 to 70 liter, and also the mixing time can be reduced down to 2 hours. So the fully automated operation of all the process steps, including the dosing of the raw materials, premixing, fine dispersing, degassing, and so on, enables to achieve better recipe accuracies, enhance process control, and in the end, a better traceability of the product. This is also a very important aspect for large-scale production of the electrode slurry. This is supported also by the inline monitoring of all relevant process parameters. So, for example, the power consumption of the mixer, all the feeding rates of the raw materials, pressures, temperatures, and so on. Furthermore, we are working on the development of an inline quality control system, this QualiP here. Basically, this system allows to inline measure the quality of the electrode slurry which is coming out of the mixer here. So these are basically parameters such as the viscosity. This is very important for the coating step, but also solid content, particle size distribution, and so on. I mentioned before the possibility to control the shear load which is applied to the product. This is very important for the dispersion of the active materials and the conductive additives. Especially for the conductive additives, for example, carbon black, you need to very accurately control the energy which is dissipated. As an example, if you dissipate too much energy, you would end up in single isolated carbon black particles, which lead to a reduced electrical conductivity in the electrode, and therefore to a lower performance of the final battery. So the target is always to dissipate the right amount of energy to deagglomerate these additives to a certain particle size in order to optimize the final performance of the electrode. And this is a point which can be done very accurately with the continuous mixing system due to the wide range of different process parameters, but also due to the very narrow residence time distribution in the mixer. Here I try to basically summarize the, let's say, the major milestones in the development of this fully continuous mixing system so far. We have started with the installation or commissioning of our test lab in China in 2012, where we did the first customer trials. So this is a small mixing system, a small extruder, which allows to process 20 to 100 liter per hour of electrode slurry. Of course, this is already quite a lot of material, but somehow if you go into continuous production, you have somewhere a minimum size of equipment which you need to have in order to be able to make a scale up later on. So currently this lab is, we're quite busy. We have many customer trials. So the lab is mainly used for demonstration purposes or optimization trials, but we also use it for internal developments of adaptation of the process and so on. Then the second important milestone, in my opinion, was the successful installation and commissioning of the first pilot scale production plant in China. This has a production capacity of about 500 liter per hour. This was done in 2015. In the meantime, we have also tested a wide range of different formulations, anode, cathode, water, NMP based, and so on, together with our customer. And currently, we're commissioning the first large-scale production plant, also in China, which has a capacity of about 3,000 liter per hour. So 2 additional factories will follow still in 2017. So with this, I've already reached the end of my presentation. I hope I could give you an insight in the topic of electrode slurry preparation. So basically, we are convinced that conventional batch mixing will not fulfill anymore the future requirements for large-scale electrode slurry production. So with the continuous mixing system, this allows you to reduce both investment and operation costs. Furthermore, due to the high degree of automation and the possibility to inline measure the process and product parameters, this allows you to improve the quality of the product, but also the consistency over time. And I've also mentioned in the end the possibility to very accurately control the shear load which is applied to the product, which in the end helps you to optimize the process for specific material properties for different formulations and so on. So with this, I'm at the end of my talk and would like to thank you for your attention.